when ancient eruptions pumped diamonds to Earth's surface. A new study offers clues to the mysteries of kimberlite eruptions, the source of most of the diamonds mined on Earth today. While diamonds might look pretty perched atop a ring, the rocks they hail from venture to Earth's surface in a journey that's anything but glamorous. Millions of years ago, some of our planet's strangest and most violent volcanic outbursts dredged from deep underground most of the diamonds mined today in the form of blue-tinged rocks called kimberlites. Unlike the volcanoes that more commonly pop up near the thinner edges of continents, the eruptions that produced most kimberlites came through the thick, stable continental cores known as cratons. Kimberlite eruptions start near the cratonic roots at least 75 miles underground, and race upward at tens of feet per second, a fiery fury driven by an abundance of carbon dioxide and water. It's like rocket fuel, said Thomas Gernon, a geologist at the University of Southampton in England who has long studied kimberlites. The turbulent flow punches a carrot-shaped pipe through the ground, ripping out chunks of deep subsurface rock, including some that are studded with diamonds. But existing research still has a giant diamond-shaped hole. Why do kimberlites form? A new study led by Dr. Gernon and published Wednesday in the journal Nature points to the ancient roots of these eruptions. He and his colleagues report that the breakup of ancient supercontinents like Pangaea and Rodinia caused deep disruptions in the flow of the mantle beneath Earth's crust, setting off the blasts. Scientists have long known that formation of kimberlites, named for Kimberley, South Africa, where they were first found, coincides with the breakup of supercontinents, but that relationship is poorly understood. One idea posits that the deep plumes of rising, hot mantle that may drive continental breakup could also fuel kimberlite formation. But kimberlites have no whiff of plume in their chemistry, Dr. Gernon said. To solve this mystery, Dr. Gernon and his team analyzed statistical correlations between continental breakups and kimberlite blasts during the last billion years. The results reveal that the two are strongly linked, but they discovered something unexpected. The eruptions were delayed, with most kimberlites having formed about 26 million years after supercontinents broke up. That sent him and his colleagues down a series of diamond-studded rabbit holes to test the strength of the link and explain the delay. The team's computer modeling suggests that as continents pull apart, hot mantle wells up in a churning convection that heats and tugs on the root or keel of a continental core. The keel drips downward like wax, producing eddy-like currents in the mantle. As bits of the keel's carbonate and water-rich rocks mix into the churning mantle, they could melt just enough to form an effervescent magma similar to kimberlites that would hurtle to the surface. The churning mantle can cause ripples at the craton's base, setting off eruptions over tens of millions of years, helping explain why many kimberlites seem to migrate toward continental interiors over such a long time. Their analysis presents a really compelling evidence base to support their model, said Janine Kavanagh, a volcanologist at the University of Liverpool in England. But the case is not yet closed. Philip Janney, a mantle geochemist at the University of Cape Town, praised the group's statistical analysis but said that the study only showed the strong influence of supercontinent breakup on kimberlite eruptions, not that it is the only important factor. Supercontinent breakups are periods marked by a tangled web of interconnected processes that sculpt the surface, and many older kimberlites also emerge around periods of subduction or continental smash-ups, further muddying the picture, Dr. Janney said. That makes it difficult to pin down kimberlite eruptions' cause, especially because no one has witnessed one of the furious blasts. We just have what's preserved on the surface today, said Ben Mather, a geophysicist at the University of Sydney. Though challenging to study, kimberlites promise to yield a sparkling window into the geologic churn deep below the surface and perhaps above, too, Dr. Gernon said. The loss of the thick keel from a continent's craton could have caused the land to bob upward like a buoy, wreaking havoc at the surface in a cascade of impacts that the team is still studying. There's still many mysteries about kimberlites that are yet to be revealed, Dr. Mather said. Kimberlites are volatile rich, occasionally diamond-bearing magmas that have erupted explosively at Earth's surface in the geologic past. These enigmatic magmas, originating from depths exceeding 150 km in Earth's mantle 1, occur in stable cratons and in pulses broadly synchronous with supercontinent cyclicity 4. Whether their mobilization is driven by mantle plumes 5 or by mechanical weakening of cratonic lithosphere 4-6 remains unclear. Here we show that most kimberlites spanning the past billion years erupted about 30 million years after continental breakup, suggesting an association with rifting processes. Our dynamical and analytical models show that physically steep lithosphere-asthenosphere boundaries, labs, formed during rifting generate convective instabilities in the asthenosphere that slowly migrate many hundreds to thousands of kilometers inboard of rift zones. These instabilities endure many tens of millions of years after continental breakup and destabilize the basal tens of kilometers of the cratonic lithosphere, or keel. Displaced keel is replaced by a hot, upwelling mixture of asthenosphere and recycled volatile-rich keel in the return flow, causing decompressional partial melting. Our calculations show that this process can generate small volume, low degree, volatile-rich melts, closely matching the characteristics expected of kimberlites. Together, these results provide a quantitative and mechanistic link between kimberlite episodicity and supercontinent cycles through progressive disruption of cratonic keels. Kimberlites are sourced from thermochemical upwellings which can transport diamonds to the surface of the crust. The majority of kimberlites preserved at the Earth's surface erupted between 250 and 50 million years ago, and have been attributed to changes in plate velocity or mantle plumes. However, these mechanisms fail to explain the presence of strong subduction signatures observed in some Cretaceous kimberlites. This raises the question whether there is a subduction process that unifies our understanding of the timing of kimberlite eruptions. We develop a novel formulation for calculating subduction angle based on trench migration, convergence rate, slab thickness and density to connect the influx of slab material into the mantle with the timing of kimberlite eruptions. We find that subduction angles combined with peaks in slab flux predict pulses of kimberlite eruptions. High rates of subducting slab material trigger mantle return flow that stimulates fertile reservoirs in the mantle. These convective instabilities transport slab-influenced melt to the surface at a distance inbound from the trench corresponding to the subduction angle. Our deep time slab dip formulation has numerous potential applications including modeling the deep carbon and water cycles and an improved understanding of subduction-related mineral deposits. Introduction. Kimberlites are mafic volcanic rocks erupted from the Earth's mantle and are the host rocks of most diamonds. 1. Kimberlites occur on every craton and have sporadically been emplaced since 3-2, yet the greatest number of kimberlite eruptions preserved on Earth today formed during the last 250 to 50 million years, primarily in Africa and North America. 3. While the distribution of kimberlites has been associated with the edges of large low shear wave velocity provinces LLSVPS4 and changes in angular plate velocity 3, these do not explain the frequency of kimberlite eruptions nor enriched radiogenic isotope signatures indicating a subducted slab component in some Cretaceous kimberlite populations. The steep subduction of oceanic lithosphere into the mantle has been proposed to drive strong mantle return flow and pulses of magmatism. 6. Yet, despite the theoretical connection between volcanic eruptions and high rates of slab flux. 7. Difficulties in estimating the volume and subduction angle of oceanic lithosphere being recycled at ancient subduction zones has thwarted any correlation with kimberlite eruptions. Previous attempts to characterize the dip angle of subducting slabs applied multivariate analysis of subduction zone characteristics to search for correlations among key parameters. However, these approaches are mostly useful for reproducing the present-day slab dip and have limited application to subduction zones reconstructed through deep geological time. Here, using a recent tectonic plate reconstruction model 15 and models of plate cooling, we revisit the estimation of slab dip from simple plate kinematic parameters that characterize most subduction zones across the globe to explore the potential role of steeply subducting slabs in controlling kimberlite eruptions in Africa and North America. Relationships between slab dip, plate kinematics and rheology. The downward pull of slabs into the Earth's mantle is the largest driving force in plate tectonics, where the bending of the subducting plate plays an important role in modulating the amount of slab pull which is transferred to the surface to drive plate motion. Since the 1980 S8, multiple studies have explored correlations between subduction angle and a number of parameters including the duration of subduction, convergence rate, nature of the overriding plate, trench length and other. Is are mostly useful for reproducing the present-day slab dip and have limited application to subduction zones reconstructed through deep geological time. Here, using a recent tectonic plate reconstruction Model 15 and models of plate cooling, we revisit the estimation of slab dip from simple plate kinematic parameters that characterize most subduction zones across the globe to explore the potential role of steeply subducting slabs in controlling kimberlite eruptions in Africa and North America. Relationships between slab dip, plate kinematics and rheology. The downward pull of slabs into the Earth's mantle is the largest driving force in plate tectonics, where the bending of the subducting plate plays an important role in modulating the amount of slab pull which is transferred to the surface to drive plate motion. Since the 1980s, multiple studies have explored correlations between subduction angle and a number of parameters, including the duration of subduction, convergence rate, nature of the overriding plate, trench length, and other.